As we're drawing structures, we also need to identify formal charges. And I know that we started talking about this the other day, but this also is very, very important, is knowing how to determine formal charges. Whenever you see something that is different from the chart here, then we have you should have a little red light go off in your head. So carbon has 4 bonds, nitrogen has 3, oxygen has 2 bonds, hydrogen should have 1. And then lone pair are also important. So these need to correlate with one another, right? Though there's exceptions with halogens, generally speaking, they have 1 bond with 3 lone pair. So when we're using Kekuli structures, we need to figure out how to designate that you have a charge somewhere. Well, if you see this little, sorry, I had the wrong color there. If you see a little circle with a charge inside, that means that there's a charge on that atom. So when you have a positive charge on a carbon, what that means is that there's only 3 bonds here. Okay, so we have something missing on that carbon. If you have a negative charge on a carbon, that means that there are an extra lone pair, or there's an extra electron by having a lone pair on that carbon. So that would be what's a negative charge. So remember, we're normally going to see negative charge on oxygen and a positive charge on nitrogen, just because that's the way things go. Okay, you've probably seen that in general chemistry as well. So remember, to determine the formal charge of something, it's the number of valence electrons from the periodic table minus, and this is all in parentheses here, the number of bonds plus the number of lone electrons, not pairs. So that's going to give you your formal charge. So I've given you some examples here. So if we see oxygen with a negative charge, the formal charge would be equal to 6, that's the number of valence electrons on the periodic table, minus, it's got 1 bond, and 6 lone electrons. So that's where it has a -1 charge. Versus nitrogen has a positive charge here. Well, it's got 5 valence electrons. It's got 0. Oh, sorry, I did this backwards. It's got 4 bonds, and this is 0, so that's okay. It's still going to total out to +1. Sorry, I just did those backwards. And so what you should do is go back and prove to yourself that that's the proper way to get those positive and negative charges on carbon. We can arrange Kekuli structures in a way that reflects 3D space. And that's one of the cool things about them. So dashes exist behind the surface of the page. So I often say that you dash back home sometimes to study chemistry. I'm sure everybody does. Wedges exist in front of the page, and the straight lines are in line with the page. So you start to see this a little bit better, and hopefully you can sort of see it in 3D as time progresses. You certainly do not need to do that right now, and realize that there's always hydrogen that is there if it's not drawn in, that's coming on and off the page, whether you realize it or not. So there's many different types of structures that exist. In biochemistry, you're probably going to see Fisher projections and Haworth structures. Talking about different structures, it's time to move on to resonance structures. And I'm going to follow this up with a video that's specific to resonance structures as well. But resonance structures are awesome things that sort of represent where the possible placement of electrons forms. And we usually see this with pi bonds and lone pairs as to like where they can actually exist, because you have to have sigma bonds. You have to have single bonds connecting a molecule, or it's no longer connected. It's no longer a molecule or a compound. So the actual structure is usually somewhere that's a hybrid in between all of the possible resonance structures for a compound. So when we're talking about resonance structures, what we're really looking at is if we were to look at this possible ways that we can put together this compound and its electrons, let's look at all those possibilities. As I said, we have to have things stuck together by sigma bonds because otherwise it's not a compound. But the other things, the lone pair of electrons, the pi bonds, those can kind of shift around a little bit. And so what we form is a hybrid in the middle that's like an average of all of those possibilities. And so one example of that is benzene. What we found when benzene was sort of like found as a molecule is that we know that it's got 3 double bonds, but in truth, they don't exist as single, double bonds. That's not the way the molecule behaves. It's not the way it reacts. And the reason why is because we can draw 2 resonance structures of this, okay? And what actually exists is kind of like a mixture of the 2 of them. And so instead of putting like double bonds around this entire inside of that that ring, we denote that there are delocalized pi electrons, and we do that by showing a little dashed line. So what that means is that the double bonds kind of like spread throughout the center of that ring. So if you want to look at it like this, if we were to draw that dash all the way around, it kind of looks like that, and that's where that circle comes from, okay? Definitely you're going to have to practice resonance structures. It is not something that naturally comes to most people. You've just got to practice it. And there are many different types of resonance structures there can be a ton of. So you just practice makes perfect on these, okay? Doing great. Thanks.